said that so in this task, we're supposed we have a linear regression and we know that the error u is normally distributed with mean 0 as usual, but now the new thing is that the variance covariance matrix of this error is omega. And omega is just a covariance matrix, n by n covariance. Right? So before that, this assumption would have been that u normally distributed with mean 0 and variance sigma squared I, which meant that we have a variance covariance matrix with the same sigma u's on the main diagonal and zeros everywhere else. Right? So we assume that all of the variances are the same, which is called homogeneity. And all of the off-diagonal elements are 0, which means that these errors are not autocorrelated. It's not autocorrelated. So correlated with itself. That this autocorrelation assumption doesn't say anything about the correlation of u with anything else, or with any other, with any regressor, with y, or whatever. No, this is the u, how is u correlated with itself, with its own past. It's not autocorrelated. But now we have this free matrix omega that can have any entries. It's still symmetric and squared because it's still a covariance matrix, but the main diagonal elements can differ, so we can have heteroscedasticity where the variances are different are large and different for each observation, and also the errors are allowed to be autocorrelated, so correlated with itself. So the error in this period can be correlated with the error in the previous period. So sometimes the positive error follows on a positive error, for example, and something like this. So this is the new part. And now we are going to show some of the issues that we get with this assumption. First, we already give you the two estimators that you could use, so you can still use the OLS estimator, but it's going to have some issues. So for that, we're going to show in A first that the OLS estimator is still unbiased using this assumption, but we're going to calculate the variance, which is going to look different from before. And then we're going to do the same for GLS, so show that this generalized least-squares estimator is unbiased, and we're going to calculate the variance. And in B, then we're going to show that the GLS estimator is more efficient than the OLS estimator, and for that we're going to show that the difference between them is positive definite. So this is going to be a lot of linearity again. Yeah, so this is the end. So under this assumption that we have this general form for the covariance matrix, the GLS estimator is more efficient than the OLS estimator, so that's going to be the result of this. And if you look at the OLS estimator, you already see here that we are going to, in both cases, so we multiply inside of our x prime x matrix, we multiply with the inverse of our variance covariance matrix, And what that does is that we are going to weight, it's kind of like we weight each and every observation in X by the variance and the covariance of the respective observation. Right? So this is kind of a weighting matrix, like the inverse of the variance covariance matrix is used as a weighting matrix to make sure that we know how important the observations are. And for example, one of the things that we're going to get is the higher the variance of an observation, the less information is contained in this observation. Right? So if there's a large variance, less observation, that this observation is going to get a lower weight in the estimator because it's less, it has less information content. For the regression line, for the beta, and this is how then in the end this beta is going to have a smaller variance, because we're going to use the information that we have, that we observe, that more efficient, because information that observation that contain a lot of information get a higher weight compared to observation that get a lower. That contain lower information. And this is we do this by weighting this, our X and Y data by the inverse of our variance covariance matrix. Okay, so that's the plan now. And I'm positive that we're going to do this well, and I think it's also, again, a good exercise for, in general, and ties very well together with what we did in exercise, on the exercise sheet 2, for the statistical properties. So we again calculate unbiasedness of this time 2 estimators, variance of 2 estimators, and then we're going to see the difference between them, which is kind of it's done differently from the Gauss-Markov theory, but yeah, we've already seen this. The first part is show unbiasedness and variance of an estimator is probably going to come up in the exam, so this is always an important step for you guys to practice. And I think the second part is more the efficiency. It's going to be it's going to take a while, so this is too long for the actual exam, but I think we can take a lot from this because it's such an important result that GLS is efficient in these cases. Okay, so let's start at the beginning. As I said, we have this. We have the 2 estimators, and then exercise 1A. So we have given the OLS estimator, which is x prime x inverse x prime y, and we have the GLS estimator, which is x prime omega inverse x prime omega inverse y. Now to show unbiasedness, remember that the first thing you always do is write the estimator in terms of the true value and the error. We've done this before for OLS, so I'm just going to write this out again. So we can write OLS estimator as beta plus x prime x inverse x prime u. Now we can calculate the expected value assumption that we have this omega variance matrix still unbiased. And so we take the expectation of this. Expectation of beta for the true value is just beta because that's not a random variable. So expectation is just the same as before. And then we have the expectation of x prime x inverse x prime u. And then we can utilize, we did this before, guys. So we utilize the law of iterative expectation by knowing that the unconditional expected value is the same as the expected value of the conditional expected value given x. So here is this law of iterative expectations we've seen before. And then we know we can take this x prime x inverse x prime out of the conditional expected value given x, because if you calculate the conditional expected value given x, we assume that x is given in that point. So we can also take it out of the expected value, and then we have this, only the expected value of u given x, and we still assume in the exercise that we have, I didn't include it, that's great, but we still assume, or in this, at this point, we need to assume strict exogeneity. So that expected value of u given x is 0. So no matter which x we observe, we always expect a value, an expected value of the error is equal to 0. So then this is 0, and the whole last term is 0, and we just get beta, so that this is unbiased. We can do the same thing for the GLS estimator, where we first write the GLS estimator in terms of the true model, in terms of the true parameter and the error. And this is done by plugging in, and we have done here, so I'm going to do it one step at a time. So this is done by always plugging in the true model for y. So this is x x beta plus u, and then we factor out the brackets so that we have x prime x omega inverse x inverse x prime omega inverse x beta plus x prime omega inverse x prime omega inverse u, like this, right? And then we see that here in the first term before the beta we have x prime omega inverse x inverse, so the inverse of this, and we have the matrix itself, x prime omega inverse x, and the product of this is by definition the identity matrix, like this. And then we're also here for the beta hat GLS left with beta, the true value, plus this term in front of the error. much the same thing is going to happen again as it did with the OLS estimator, but for completeness, I'm just still going to write it out. So now we take the expected value, we have beta plus the expected value of x prime omega inverse inverse x prime omega u. Then we use the law of the Treppe expectations to get the conditional expected value in here, so that we can afterwards factor out the x's from the expected value. Like this. And make sure all of these omegas have an inverse. And then we still have beta, so pretty much same thing as before. This is why I said we do this often, and in the end I expect you guys to be able to do this in the exam. We factor out, we can take out everything that is constant out of the expected value, but in this case we have all of the x's, because this is the conditional expected value given x, and also omega inverse, because that's the variance, and the variance is not the random variable. Right? So this is the true variance of our error. It's not a random variable. What would be a random variable would be the estimator for this variance, right? So that's always the question in previous economics is always what is our true value, what is our theoretical value, and that is fixed, that's not a random variable. And all of the estimators for these values are random variables. Okay, so omega also out of the expected value, so we get x prime omega inverse x inverse x prime omega inverse conditional expected value of u given x, and still again this thing, the only thing that we need to assume here is that this thing is 0, so also here we assume strict exogeneity. So the same thing as before. So under the same conditions, and then the whole thing becomes 0, right? So what do we learn? Well, this is also unbiased. So what can we conclude here? Before, under strict exogeneity assumption, we both estimators, OLS, so ordinary squares our usual everything, and the GLS are unbiased. So both are unbiased estimators. If you just think back on what we discussed in exercise, on all of the exercise sheet 2, when we talked about the statistical properties of this of the OLS estimator, and there we showed that the OLS estimator, under the certain assumptions, under the previous assumptions, was the best linear unbiased estimator. So if our assumption is true, so under, and the GLS estimator is now also a linear unbiased estimator, right? So it also falls into this class. So under our standard assumptions for with homoscedastic and not orthocorrelated errors, the GLS estimator would have a larger variance, right? Because we showed that every linear unbiased estimator has at least a variance whole